Hello everyone and welcome. In this video we are going to discuss how to design chat applications like WhatsApp and Messenger. Okay. WhatsApp and Messenger are the messaging application that connects billions of people around the globe. Here are some stats about WhatsApp from 2020-2021 timeline. There were approximately 2 billion active users on WhatsApp, and on average a user spent around 19 hours on monthly basis on WhatsApp. And WhatsApp used to handle around 100 billion messages every day. So this is the scale we are going to design for. Okay, let's see what are the functional requirements for these kind of chat applications. Very first thing is that this our system should be able to support a one-on-one chat or group conversation. Okay, then it should also support acknowledgement receipts about messages, like the message has been sent, the message has been delivered, or the message has been read. Okay, next, the chat application should also support sharing media files like images, videos, and PDFs. Okay, any other kind of media files also, document or anything for that matter. Then it should be able to notify users that they have received messages. So let's say when user is not active on the chat application, he does not have the chat application open at that time. If the user is connected to internet, he should be able to receive message that receive notification that he has received a message. Okay, and the system should be able to support the store the chat messages until they are delivered successfully. So it should the system should be able to store these messages persistently on persistently somewhere for a default amount of time, let's say 30 days before the messages are delivered. Okay, so let's say a message is supposed to be delivered to a user B. He is offline, so the application should be able to store this message in persistent storage for, let's say, 30 days. If even after 30 days the user B does not come online, then the system can delete this message. Okay, so these are the functional requirements. Now let's see what are the non-functional requirements. So very first thing is the consistency. The messages should be delivered in the order they were sent. Okay, and users should be able to see same chat history on all the devices. So ordering of messages is important. The user should be able to see the messages in the order in which they were sent by the sender. Okay, and the chat history should remain consistent on all the devices. Okay, then there is low latency. The chatting should feel real time. Okay, there should not be any delay while sending or receiving the messages. That is very important for user experience. So users should receive and should be able to send messages with low latency. Okay, now that we have discussed the functional and non-functional requirements, let's see how would a simple design for this chatting application look like. Let's suppose that there is a user A and he wants to send a message M to user B. Okay, how would this happen? A wants to send the message. There is some server sitting in middle which will coordinate all this. So let's say A wants to send a message, so A will initiate a communication channel or a connection with the server. Okay, it will send after initiating the connection, it will send the message M to the server. Okay, now once the server has received message, it will check if user B is online or offline. If user B is online, in that case the server will have to initiate connection with user B. It is important to note that server will have to initiate the connection because B does not know it is going to have some messages or not. So server needs to initiate a connection with B and send the message M to B. Once B receives the message, it will send back the acknowledgement that I have received the message, and the server will send this acknowledgement back to user A. Now this was the case when user B was online. Let's say user B is offline. In that case, the server is supposed to store this message onto persistent storage, and it will need to store it till user becomes online. Okay, so this is how simple design of chatting application looks like. Okay, now there are some certain things. Let's try to dig deeper and see how will we expand this to a real-time full-fledged application. So the first problem or the first thing that we need to consider for this particular design is what protocol should be used for communication between client and servers. Here A and B are our clients, and we have a server. You see there is a connection set up between client and server. What protocol should be used for this connection? Okay. Before trying to understand what protocol, let's discuss about the protocol that is in general used between client server communication. So in general, normal client server communication uses HTTP, that is hypertext transfer protocol. Okay, now it is a request response based protocol. What does that mean? Every time client needs to send data to the server or request data from the server, it will have to set up a new connection. Very first thing, every time it needs a response from server, it will have to set up a new connection. Okay, now it sends a request for data to the server prepares the response and sends back the reply with data. Okay, once this is done, the connection gets closed. So once the request has gone, reply has come, the connection would be closed. Okay, now with this request response model, what problems will we have? So in case of WhatsApp or any messaging application, client, if we use HTTP, the client will have to ask server for data. Client will always have to initiate a new request and check for data. Very first thing, every time client needs to check if there is a new data available for it, it will have to initiate a new request. That is one thing. Then it is a stateless protocol. What does that mean? Every request client makes to server, a new connection has to be set up or initiated, and for every new connection there is a delay. So we need something which once the connection is set up, it should remain in that state, it should not get closed. But here in this case, with every new message we'll have to set up the client will have to set up new connection with server. Okay, first thing was the client will have to again and again ask, is there a new message for me, is there a new message for me? That is one thing. Second thing is, for every request like this, it will have to set up a new connection with server. Okay, third is HTTP works only one way. So in that in one connection there is going to be only one request and one response. So only client will be, if client has set up connection, only client will be able to send request, and only server will be able to send respond. But in WhatsApp we need a full duplex connection. That is, the client should also be able to send message whenever it wants. Server should be able to send message whenever it wants in single request. Okay, in multiple requests they can do in HTTP, but we want that to happen in a single request. Okay, so these are the things. So what are the problems with HTTP, or rather what things we want in WhatsApp? We want in the protocol we want in WhatsApp needs to be stateful. That means it needs to know what has happened before, which message has been sent, and what is the response for that. We do not need to have, or we need something that does not need to set up a new connection every time. So HTTP does not support this, but WhatsApp needs it. Next, we want that the connection should be full duplex. That is, both server should be able to both client and server should be able to request and respond. HTTP does not support it in a single connection, but we need that for WhatsApp. Then we want low latency. Since for every message we'll have to set up a new connection, it will add latency to the message replies and request. Okay, but WhatsApp needs it. Then we need some mechanism such that server should be able to push the messages. Whenever server has a new message for some client, it should be able to push the message. But in HTTP, client will have to request every time, is there a new message for me? So this is not suitable for WhatsApp. A very last thing is that we need a persistent connection. Okay, once the connection is set up, until user goes offline, we need the connection to be in that state and the communication to go on. But that is not the case with HTTP. Once a request and response has been sent, it will close the connection. So this is also not suitable for WhatsApp. So these are the problems with normal client server communication protocol, HTTP. So what protocols is ideal for communication between client server when we need real-time communication? Okay, for chat application, the answer is WebSockets. Okay, now let's see how do WebSockets work. So let's first discuss how connection is set up in a WebSocket. Let's say there is a client and there is a server. To establish WebSocket connection between client and server, client will first send HTTP request upgrade. So in the request itself, it will initially send an HTTP request, and in the request itself it will request for connection upgrade. Okay, so client sends up this HTTP request to server. Server will respond with acknowledgement saying that okay, I am good to switch the protocol. Okay, once this response has been sent by server, they set up a WebSocket connection. Once the WebSocket connection has been set up, anytime a client can send message to server and anytime server can send message to client. Okay, so this is a one-time setup. So the delay would only be added once. Post the connection has been done, they can anytime send request and response. Both can initiate request, both can initiate response, whatever way they want. Okay, so WebSocket enables single persistent connection. It is bidirectional because both client and server can send request and response, and it is low latency because connection setup is going to happen only once. So these characteristics make WebSocket suitable for chatting or messaging applications or any application that needs real-time updates like multiplayer game. Okay, in that case also WebSocket is the suitable protocol. Let's discuss how would the high-level design of our system look like. Okay, I would suggest you to take screenshot of this diagram. It will be handy for our further discussion. So let me list down what all services do we have. We have something called as socket connection handle service. Then we have connection manager. We have other microservices like chat service, group service, media service, notification service, and we have message store service. Okay, and then we have globally distributed network of CDNs. Let's discuss each of these services in detail. Okay, so very first thing that we need in our system is something that maintains a persistent WebSocket connection with our clients. Okay, so that is what connection handle service, socket connection handlers do. Okay, this service maintains persistent WebSocket connection with our clients. Okay, now since there would be many clients who would want to maintain persistent connection with our system, we'll have an array of clusters that would be running this service. Okay, next is connection manager service. Now connection manager service maintains a record of which client is connected to which server. Okay, this record is maintained in Redis. So for record maintenance, we have a service that is connection manager service, and the record maintenance is done in Redis. Okay, now once the socket connection is set up between client and socket handler, client keeps sending heartbeats to the socket connection handler at regular intervals. That is how socket connection handler would know that yes, this particular client is online. Okay. Now connection manager also maintains record of when was the last heartbeat received from the client. So it will maintain client ID, which socket connection handler or socket handler service it is connected to, and I mean the service would be same, but which server who is running this service is it connected to. It will maintain the timestamp when the last heartbeat was received from a particular client. Okay, now this timestamp can be used to show whether a client is online, offline, and if he is offline, when was the client last seen. Okay, now let's consider A wants to send message to client B. Okay, there could be two scenarios in this. B could be either online or he could be offline. Okay, A wants to send a message M to B. Now the message would come to the chat service. Chat service will fetch info from Redis to see which socket handler is B connected to. Okay, if B has an active connection, it will be seen as online. B has chat open and he's connected to any socket handler. It will be seen as online, and chat service will simply forward this message to respective socket handler, and B will receive the message. Along with this, B will also send a message to a message queue to persist this message that this message has been sent to B. Okay. In case if B is offline, the chat service will add the message to message queue, from where it would be picked by message store service. In this case, it will be picked by message store service and put in persistent storage, so that when B comes online, it will be able to send the message to user B. Along with this, because B is offline, this message will be picked up by the notification service from the message queue. This service is responsible for sending push notifications to offline users. So in case if it is offline, the message would also be picked by notification service, and it would be sending notification to B that you have received a message. Here offline means the user does not have chat window open. That is why it is offline. Okay. Now other case would be the message that A needs to send is for a group. In this case, chat service will fetch list of all the members from group service. Okay. Group service handles responsibilities like creation of groups, adding members to groups, etc. So all the group related responsibilities will be handled by group service. Now once the chat service has list of all members, it sends the messages to each one of them, similar to case 1. So once it has got a list of all the members from group service, it will send the message similar to the way it was trying to send message to user B. It will have all the cases, like all the list of members could be offline or they could be online, so it will handle them accordingly. Okay. Message sent that is being sent may also contain media files like audio, video, documents or PDF. Okay. These files are not directly sent as part of message. Media service is responsible for uploading and dealing with media files onto blob storage. Okay. So, offloading of media files responsibility from chat service or chat servers helps reducing bandwidth utilization on this servers. So when a client sends a media file in a message, this media file is uploaded onto CDN server that is closest to the client. Okay. Only the media file link is sent as a part of message. Now once the media file is uploaded onto CDN, it is picked by media service and it is persisted over the blob storage. Okay. Since the CDN are close to users geographically, it helps reducing upload and download latency for these media files. Okay, now let's see what all things do we need to store while designing a chat application. So very first thing is that we need to store information about users, and that information would be username, user ID. The profile picture of URL will of course store URL here, because the actual picture would be stored in blob storage again, and we'll need user description. So these are all the things that we need to store about user. Then about the group. For a group, we'll need to store the group name, the group ID, again the profile picture URL of the group, because the actual picture would be stored in S3. We'll need the group description, and we'll need the conversation ID where the conversation is happening. So the conversation is stored in some separate place. That is why we need conversation ID that can be linked to this particular group. Then we'll need a list of group members. So for that we'll need group ID, member ID, and for each member ID we'll need to store what is the role of that member, if he is an admin or a regular member. So this is the information we need to store about group members. After this, very important thing, we'll need to store conversation or the chat. Okay. For that we'll need to store conversation ID, and we'll need to store messages. So we'll store message For each message we'll need to know what is the sender ID, the actual text of the message, the timestamp at which the message was sent, and the media URL. So message could contain docs or PDFs or videos or images. So we'll need all those URLs. So that is how a conversation would be stored. Okay. For user group and group member information, the data is pretty structured and we can very easily use relational databases like SQL. The main thing here is how do we store the chat or the conversation. So in order to understand what should be used for storing these conversations, we need to understand the characteristics of this conversation. Okay. So very first thing is that we are going to have a lot of write requests, and we'll need low latency reads. So the storage needs to have high write throughput and low latency reads. It should have high availability, of course, because there would be always write requests and there are going to be always read requests, so the availability needs to be high. Then the access pattern is going to be like this. Most often we'll have we'll need to fetch latest n messages. Let's say we'll need to fetch latest 50-60 messages always. So this is going to be our access pattern for the storage, because whenever you open the chat application, the very first thing you see is the latest 50-60 messages on that. And also the ordering of the messages should be preserved. So these are the characteristics of the chat storage, or these are the characteristics we'll need for storing our chat or our conversation. Okay. Now what database should be used for this? So it is obvious that the chat message format is not I would say very strict. It keeps on changing. A message may or may not have text, and it may or may not have a lot of media files. Okay. So a message may contain one or two media files, or it can have a lot of media files, or it may not have any media file at all. Okay. So the format of chat, format of message keeps on varying. So obviously SQL is not going to be our choice here. We'll have to go with NoSQL. Okay. But again the question arises, which NoSQL database to use? Let's consider document DB and white column databases. Let's first see what happens if you use MongoDB. So in MongoDB, each message would be stored in this format. So each message would be stored in a document which will have chat ID, message ID, user ID, the text of the message, timestamp, and maybe we can also have media URLs here. Okay. Now in this case, the chats would be, so if whenever we want to fetch all the latest messages from a particular chat, we'll query the chat ID, and we'll need to sort the messages based on timestamp or the message ID. So this sorting at the scale of millions and billions would be extremely slow. So that is one problem with this. What happens if we use Cassandra? If you use Cassandra, the tables will be partitioned based on chat ID. So for each chat ID we'll have a table, and this table would be ordered by message ID or timestamp ID. So we could do one thing, that we can incorporate timestamping in the message ID itself. So using message ID we will know which we will be able to know the ordering in which the messages were sent. So let's say message was sent on 12th of July and at 1 p.m. So we could use this timestamp itself as message ID. So we'll naturally know the ordering of messages. We'll need not have a separate field or column for knowing ordering. So timestamping feature will incorporate in the message ID itself. Now if we use this message ID to order all the messages in the table, then we'll naturally have all the messages in sorted order. Okay. So this incorporates two things. If we have sorted the messages by timestamp ID, our inserts would be very fast, because each incoming message would be simply uh, append operation. So whenever we get a new message, we'll simply have to append that to the database, and reading from the database is also going to be very fast, because we'll always need the latest 10 messages or latest 50 messages. Okay, so fetching latest messages would also be very easy, because we'll not need sorting here. So this is how reading and writing both will be very fast. So Cassandra is actually best suited for efficient read heavy data, especially when the data is time series data or log style data. So that is why will be going with Cassandra here. Cassandra suits our requirements for storing the conversation here. So we'd be going for going with Cassandra for storing our chat messages. Okay, now let's deep dive and see if we have missed anything. um, if you see here, the components for storing database or components for storing the ordering or mapping of which client is connected to which server, we are using Redis and Cassandra. So these kind of databases are like they ensure availability, fault tolerance, so we don't need to worry about these things while using Redis and Cassandra. For microservices, we'll have microservices we discussed, like connection manager, chat service, group service. These microservices will be replicated on multiple servers. So even if one server goes down, we'll have another servers that can serve this incoming request. Okay, now we have not discussed how will we incorporate message delivery indicators, like message sent, message received, and all this. So let's discuss that. Suppose a user tries to send a message, the message will be received by chat server. Okay, now chat server will send this message to message queue, and the chat server will itself send the acknowledgement back to the user's app. So when the acknowledgement from chat server is received by user, his chat application will show that the message has been sent. Okay, in case if while sending the message user A was offline, then it will remain in pending state on the chat application on the user or the client side. So that is how user is going to know that the message has been sent. Now once the receiver who was, let's say, offline comes back online, the chat server will receive notification that this user has come online, and it will know that it has a message pending to be delivered. So the chat service will push the acknowledgement to message queue that this person has come online, and message queue will fetch any pending messages to be received by this particular user, and the chat server will receive these messages, and chat service will send back these messages to that particular user. Once this messages has been received by the user, the application on the user side will send back the acknowledgement to the chat server that the message has been delivered. The same acknowledgement would be forwarded from chat server to the user who had sent the message, and the application on the sender side will show that the message has been delivered. Similarly, when the receiver opens the chat window and sees the message, again the chat application would send the acknowledgement back to the chat server that the user has read this message. This acknowledgement will be sent back to the sender by chat server that the message has been read. So that is how we incorporate message delivery indicators. Okay. Another thing we need to discuss is that media file storage. Okay, since users would be sending a lot of media files, our media file storage requirement would be very high, and we need to think upon the measures that we can take to reduce this media file storage requirement. Okay, let's discuss how it can be done. So very first thing is that before uploading any media file to content delivery network, the app can give an option to user if you are okay with sending a compressed file for this particular media file, or you want to send an HD high definition version of this particular media file. So mostly users opt for a compressed version of media files that can help us reduce the storage requirements. So this option is for users whether they want to send high definition file or compressed media file. So this is one way we can reduce the media file storage requirements. Another way is that another thing that we need to consider is that if you see WhatsApp, you will see a lot of duplicate media files in multiple conversations, right? So we need to have a check if this media file has already been uploaded on our CDN or our S3 storage or not. So how can we check that? Before uploading any media file, the client side's application can compute the hash on that media file, and it can check if that hash value is already present in our database or not. Okay, so it can have a mapping of hash value and media file, actual media file. When it computes the hash on the client side, it will send this hash value to the database and check if the hash is already present. If the hash is already present, then it will not actually attach the media file, it will attach the associated media file URL in the chat message. And if the hash is not already present, then it will upload the actual media file onto the CDNs. So that this is another way of deduplicating the media files in our system. That is pretty much it. I hope you would have understood this. Thank you.